Okay, so today I'll talk about the surface anchoring mediated hierarchical self-assembly of orientational ordered plasmonic nanoparticles in liquid crystals. I'm coming from University of Colorado, Department of Physics, and also Liquid Crystal Materials Research Center. We all know that small is different, and if you look at properties of tiny gold nanoparticles and big pieces of gold, for example, we see clearly the difference. In the case of gold nanoparticles, you can see in here, dispersed in different isotropic solvents. We can see colors that come from the fact that we have surface plasma resonance present due to the properties of tiny gold nanoparticles. And so as you would go from left to right, in here we have spheres, short rods, medium length rods, and long rods. And you can see that colors change. And as I already mentioned, the reason is surface plasma resonance property. If we have just spherical particles, then we have a single peak at about 525 nanometers. But if instead we have rod-like particles, we have an additional peak, the longitudinal surface plasma resonance peak at somewhat longer wavelengths, and the wavelengths actually depends on the aspect ratio of the gold nanorod that we look at. So why is this interesting? Well, if we are able to control the organization of such nanoparticles on nanometer scales, we can actually design properties of materials and form nanocomposites that would have behavior, physical behavior, very different from all existing materials. Right? So one example could be, for example, metamaterials that can allow us to even achieve negative index of refraction. Right, which was obviously thought to be impossible for many decades, but was actually demonstrated not too long ago, experimentally and theoretically. And so you can see examples of metamaterial structures in here, where we can have the control of organization and composition on nanometer scales, and this can allow us to manipulate optical properties or some other properties. As I already mentioned, one property that can be achieved even is negative index of refraction. So how could we possibly fabricate such materials? Well, one way to do it would be to use nanofabrication, and it's always getting better. But it's still quite expensive, hard, and it's a process that's not scalable. So if you nanofabricate really interesting materials that allow you to study physical properties, it doesn't still mean that you would be able to make devices out of them, because the quantities will be really tiny. On the other hand, one could use self-assembly of nanoparticles, like the gold nanorods that I showed you before, and if we could control organization of those particles precisely, both orientational and positional ordering, the way we want, we could then again fabricate interesting nanoscale materials. And so, as you know, the self-assembly is the basis for biological processes, and can be quite sophisticated. Even life would be impossible without it. So let's see if we can utilize self-assembly to achieve orientational ordering or other types of ordering on the nanoscales. So in the work that I'll present, we will use liquid crystals, mostly nematic liquid crystals and also cholestatic liquid crystals. And so I guess all of you are familiar with them. They stand in between the crystalline solids and isotropic fluids and share properties of both. They can flow like isotropic fluids do, but at the same time they have anisotropic properties similar to those of solid crystals, and uniformly aligned nematic liquid crystal is essentially optically a uniaxial crystal, optical crystal. And so in here you can see a type of molecules, the chemical structure of molecules that can form those phases. Now we can think about putting different types of inclusions into liquid crystals, right, in order to change properties. And so the size matters in this case. And some time ago, about 1.5 decades ago, there have been beautiful studies on the introduction of micro-sized colloidal particles into liquid crystals, where one can control surface boundary conditions. And for example, if you have such a spherical particle that you can see in here, you impose very strong boundary conditions, you realize that molecular alignment around this particle looks like that around the point defect. And then if you introduce this colloid into a liquid crystal with uniform alignment, you also introduce a point defect that compensates that topological charge due to the particle itself. And so different types of configurations can occur, dipolar and quadrupolar configurations, where in the other case one can also have a disclination ring. And so you can see that the symmetries of those structures are different. In one case it's axially symmetric, and one mirror plane in here is broken, while in the case of quadrupolar structure it's present. There is a beautiful analogy between those types of particles in a liquid crystal medium and electrostatic dipoles and quadrupoles. So if you put many of such particles with dipolar structure, you can see formation of chain-like assemblies. If you put particles with quadrupolar tangential boundary conditions and quadrupolar symmetry of distortions of the vector field, you again can see self-assemblies, but those are now somewhat different. And so one could think about using those interactions that are mediated by elasticity of liquid crystal medium. And so those particles interact with each other to minimize the elastic energy, the cost of distortions that are produced by those particles. And so by arranging themselves into different chains, they can minimize overall energy. And so one could think about self-assembly of those particles into different useful configurations. But in our case, however, we have much smaller particles, right? So in order to be able to control properties, optical properties, we would need to have particles that are much smaller than wavelengths of light, right? And so what I'll demonstrate today is that as we go to much smaller sizes of particles, the physics can be somewhat different. And also what we will do is we will deal with the anisotropic particles, so rods and platelets in particular. And so I'll demonstrate that as we go to small enough particles and weak enough boundary conditions on surfaces of particles, we can achieve uniform dispersions of such nanoparticles in liquid crystals when we still can impose orientational ordering and organize them into long-range orientationally ordered structures. So in all of those studies, it's very important to properly define surface boundary conditions, as I already mentioned. And this can be done in a number of different ways, the chemical modification. Everything will depend on the type of liquid crystal that we will use. And in our studies, we will use both lyotropic and thermotropic liquid crystals. And then here you can see gold nanoparticles that are Seil-capped, 2 nanometer gold nanoparticles dispersed in a cholesteric liquid crystal that are well separated from each other, right? So they do not form any sort of chains that you could possibly see, and that means they do not aggregate. They are indeed in dispersion. So those images were obtained by means of freeze fracture transmission electron microscopy, and they give a direct evidence of such a dispersion. But as I already mentioned, most interesting particles for us will be those with anisotropic shapes, because with those we can actually design those new material properties that are not present in naturally occurring materials. So in here you can see some examples which were of particles which were synthesized in our lab. Those are triangular platelets, only 5 nanometers or so in thickness, but the lateral sizes can be varied from 100 nanometers to almost microns, and you can grow nanoplatelets in the form of triangles, hexagons, nonagons, and so on by just controlling kinetics of the crystal growth in the case of those nanoparticles. One can also obtain the gold nanorods and nanowires with different aspect ratios, and here you can see just some examples, right? So now if we have those anisotropic building blocks, because they are anisotropic, and if they could be well dispersed, a natural question arises, why would not we just simply form a liquid crystal phase out of those anisotropic nanoparticles, right? We know the Onsager theory, right, which tells us that as long as we have anisotropic enough nanoparticles, like rods, at high enough concentrations, the competition between the translational and orientational parts of entropy should lead to spontaneous orientational ordering, right? Just because of excluded volume interactions for such anisotropic nanoparticles. And so, as you know, the Onsager theory predicts that, for example, if you have nanorods or any kinds of rods, well dispersed due to static or entropic, in other words, interactions, at a certain critical concentration, we will spontaneously obtain an emetic structure, right? And one could also obtain smectic configurations and some other higher concentrations and so on. But the critical concentration for orientational ordering is roughly 4 ratios of diameter to the length of the rod, right? So you can see from this that one really needs to have pretty highly anisotropic nanoparticles with pretty large aspect ratios. Now, if you recall the spectra that I demonstrated to you in the very second slide of my presentation, in order to have surface plasmon resonance in the visible part of spectrum, so that we can control optical properties with those nanoparticles, we do need to have very small aspect ratios of gold nanorods or other anisotropic nanoparticles of the order of 2 or 3. And then if you substitute such an aspect ratio to this simple estimate of the critical concentration, you realize that you can never obtain liquid crystalline self-organization of those weakly anisotropic nanoparticles. So this approach would not work. The other approach...
The estimation would have failed for such particles, right?
Right, because you would need to have more than 100%, right? So,
no, I mean the estimation.
And that too, yeah, that's exactly the case too. So also this estimate is working for highly anisotropic particles, but in the limit where this aspect ratio is small, the theory would not work as well. Yeah, but now, however, if you the other approach could be using liquid crystal medium to organize those nanoparticles. And so in here you can see an example of nanoplatelets that I showed you before. If we put those into lyotropic liquid crystals, as that you can see depicted in here, they tend to align with large area faces parallel to the far-field liquid crystal director. And then depending on the thickness of the platelet, we can have 2 different regimes of alignment. In one case, they still can rotate around the director, as depicted in here, and also around this axis perpendicular to large area phase. In the other case, when those distortions are larger for somewhat thicker particles, only around this axis parallel to the far field director. So you can see we can achieve some forms of alignment of such particles in liquid crystal medium. Also, if we put in thermotropic liquid crystal and treat the boundary conditions for perpendicular surface alignment, then the defect line analogous to that we saw before for a sphere appears, and those particles align with large area phase perpendicular to far field director, right? But now let's look at rod-like particles. And so if we disperse those gold nanorods into, so we have seen already example of platelets, the same can be also achieved for gold nanorods. And here is an example of how we do it for the gold nanorods that are capped by CTAP. This is a type of surfactant you can see in here that's actually used in the process of synthesizing those nanoparticles. And then we introduced it into lyotropic liquid crystal phases that are formed by cylindrical micelles that are also made of the same surfactant, right? And so now, as you can see depicted in this cartoon, we can achieve orientational ordering of those gold nanorods with relatively small aspect ratios in both nematic and columnar hexagonal phases. So we can assure this is the case by doing freeze fracture transmission electron microscopy imaging. So in here you can see just imaging of nanorods obtained from isotropic dispersion. In the case if we have this lyotropic liquid crystal, freeze very quickly, then fracture, and use TEM microscopy to probe orientational ordering of gold nanorods, we can see that they orientational order along the far field director, as we can see based on the replicas in this fracture image. So the other way of probing the ordering of those nanoparticles in liquid crystals is to use optical characterization, right? And so in here we again take an example of gold nanorods, and so if they are dispersed in an isotropic medium, isotropic solvent, you can see we have two plasmon resonance peaks, one at 525 nanometers and the other one at longer wavelengths. And however, there is no polarization dependence in this case of those kind of extinction spectra. We can use FDTD numerical modeling and obtain similar results by means of numerically solving the Maxwell's equation, and so we can see that there is a good agreement between the types of spectra we achieve in those two cases. However, if we now disperse those gold nanorods in a lyotropic surfactant-based nematic liquid crystal, we can see that the spectra are highly polarization dependent, right? And so we see the same two peaks as before, but the strength of the two peaks in extinction spectra is highly dependent on polarization. As you can see, for different angles, spectra depicted here are obtained for different angles between the far field director and the polarization of the used light. So what is it that we have? Do we have any sort of crystal of gold nanorods in liquid crystal, or is it also exhibiting some kind of liquid crystal-like ordering? So we can do again numerical modeling, FDTD computation by assuming that we have a perfect crystal-like ordering with scalar order parameter equal to 1, s equal to 1. And so in this case, we see that we indeed would have a very strong dependence of the two SPR, surface plasma resonance peaks, but it's somewhat different from that what we see in the experiment, right? Because giving us an idea that likely scalar order parameter is not equal to 1, but it's lower. So we can also not only align those type of liquid crystals by boundary conditions, but also by magnetic fields. And so in here you can see two spectra experimentally taken for polarizations of incident light parallel and perpendicular to far field director. And so you can see that we can see one peak for one polarization, the other longitudinal peak for the other polarization, and this one is weakly pronounced in here. Now this is consistent with the simple numerical modeling, and again this one here was done for scalar order parameter equal to 1, but in experiments, as you can see, we likely have somewhat lower value of scalar order parameter. Now, this type of magnetic alignment and realignment gives really very good quality of dispersion of such anisotropic nanoparticles on very large areas of the order of centimeters or so, and in principle one could go even to larger areas, as you can see from those polarizing microscopy textures. So the quality is quite good. Now, I don't know if you could make it darker a bit. You can see that we can achieve also alignment of gold nanoparticles even in the case if we have very dilute dispersion. So those are individual gold nanoparticles. By simply comparing the scattering images obtained in the dark field microscopy for two different polarizations, we can see that the signal is polarization dependent, and by accumulating the scattering signal for long periods of time, we can see pretty strong polarization dependence even for individual particles undergoing Brownian motion in such lytropic liquid crystal dispersion. So those spectra were obtained by means of dark field microscopy, as depicted in this schematic in here, by using a dark field condenser so that no direct light goes to the camera here, but only scattered light can pass through, and then we can probe polarization dependence of light that was scattered by those gold nanoparticles. So we can see from what I demonstrated that indeed we can obtain well dispersed gold nanoparticles, gold nanorods, nanoplatelets in liquid crystals, and the question is, what are the physical underpinnings behind? So let us consider two different possibilities. And I'll start with the possibility that we have strong boundary conditions, a strong tangential anchoring on the surface of gold-like particles. In this case, it's very easy to see that we should expect the ground state alignment of those nanoparticles with the length of the nanorod being along the far field director, because in this case we minimize the strengths of elastic distortions in the liquid crystal director field, which would be only at the edges of the particles, right, at the two opposite ends of the particle. However, if such a rod would be aligned at some angle or perpendicular to far field director, those distortions would persist along the entire length of the particle, and so clearly this configuration would be of lower elastic energy, which we can calculate by simply using the Frank-Ozin expression for the elastic free energy, which I think is probably familiar to you, where we have splay, twist, and bend terms in the elastic free energy that tell us about the cost of distortions due to splaying, twisting, or bending director field, in our case around those particles. And so later we will also deal with cholesteric liquid crystals. In the case of cholesteric, there is this additional term in here, which is due to chiral nature of those media. Now, so if aligning the rod is along the far-field director is minimum energy, how can we estimate the elastic energy cost and the elastic torques due to deviation of the rod from that equilibrium orientation? Well, this was actually done, this kind of estimation very long ago by Dejean and Burchard. So again, they started from the expression of elastic free energy that I already demonstrated to you, but consider it a situation of one elastic constant approximation where K1, K2, and K3 would be equal to each other. And then also they used electrostatic analogy in order to obtain this type of expression for the elastic free energy, which was later also calculated for the rods of different aspect ratio. And so by using this estimate, where theta is the angle to which we rotate the rod from the equilibrium orientation, we can see that for typical values of length and radius and also elastic constants, we obtain the elastic energy difference much larger than K Boltzmann T, even for pretty small angle theta. So this means definitely the elastic energy would be sufficient to align those gold nanorods, right? And but the question is this the actual mechanism, the actual physics that leads to the behavior that we observe? And so in order to give the answer, we will need to do a more quantitative comparison of predictions of such a theoretical model and the experimental results. So now let's look at the values of scalar order parameter which we can measure experimentally. And so the scalar order parameter for liquid crystals or gold nanorods in here as well will be defined as the expectation average value of second Legendre polynomial of cosine theta, where theta is angle between the axis of the rod and the far-field director. And so now the distribution of gold nanorod orientations should follow the Boltzmann statistics, and based on the predictions of Dejean-Burchard theory, we can calculate those values of sigma and C coefficient in here, and actually this expression is taken by later modification of Landau-Dejean of Burchard-Dejean model that I showed you for rods of relatively small aspect ratio. And so if we now calculate the scalar order parameter and also plug in the values of the elastic constant and the size, the parameters of the rods, what we can see is that the scalar order parameters that we would expect in this case would be pretty large, right, approaching unity. And this is not what we see in the experiments, because what we observe is somewhat lower values of order parameter of the order of 0.7, which we can simply calculate also from such spectra, extinction spectra that I already demonstrated. And so also what we can do is we can do numerical modeling of the expected extinction spectra for different values of order parameter going from 1 to somewhat lower values, and then calculate the extinction spectra for those values of order parameter and compare them to experiments, and we see that this model does not fit that well to the experimental observations. So what we will do instead now is we will consider the case where we do not have strong elastic distortions as before, and we do not have strong boundary conditions, but instead we have weak boundary conditions so that you barely distort director field around those gold nanoparticles, and instead the liquid crystal director will meet the surface of gold nanoparticles at different angles. So this actually makes sense because the nanoparticles in here are smaller than the so-called anchoring extrapolation lengths, which can be estimated in the range of 100 nanometers to 1000 nanometers for those kind of interfaces, and was measured before experimentally, while the nanoparticles that we have are actually smaller than this range. They are only 50 nanometers in length and 25 nanometers in diameter or so. And so if this is the case, this model actually might work better. So let us see what will happen. You know, as you can see, still because of the anchoring boundary conditions, although it's weak anchoring now, we could see how one could minimize overall free energy by aligning those gold nanoparticles along the far-field director as depicted in here. And so now we can use the simple Rapini popular model for describing surface anchoring boundary conditions, and again calculate calculate the overall free energy for different orientations of gold nanorods, and then the angular distribution. And so this is the type of distribution we get in this case. And if we calculate now the scalar order parameter by assuming this simple model, we get this expression, this type of dependence on sigma, right? So now you can see that everything depends on the actual values of W strongly. So in order to verify whether this model is appropriate, we will want to see this model work for physically appropriate values of surface anchoring coefficient W. And obviously for the length and radius of rods that we actually use. And so indeed it works quite well. If we take experimental value of scalar order parameter of 0.71 that we can take from a measure from those extinction spectra, and if we take the length and the rod radius, you know, for a particular example that of experiment that we had, if we plug in all of those values and also anchoring coefficient that was measured for similar types of systems, what we get is what we get, you know, is indeed that this works for values of anchoring consistent with those measured experimentally, right? So this would be the dependence of scalar order parameter on this parameter, the dimensionless parameter that I showed you, sigma, and this would be the actual equilibrium angular distribution of rod orientations in such a liquid crystal system, right? So you can see it's centered around theta equals 0. So on average, just like molecules or micelles in liquid crystal, those nanorods align on average along the far-field director, but not perfectly. It's soft matter system, right? So there is an angular distribution of those orientation, and this corresponds to a scalar order parameter of 0.71, which is consistent with experiments for the proper value of the anchoring coefficient, right? And so now we can disperse more and more gold nanoparticles, you can see in here, with pretty small aspect ratios and align them in those media. This leads to really new properties, right, that liquid crystals themselves did not have, and that gold nanoparticle dispersions did not have on their own. Because if you now use polarized light, you can see that the extinction spectra change. Before I showed you spectral version of this dependence. In here you can see pictures, you can see color changing, right? This is because of polarization dependent surface plasma resonance and those two different colors are respectively for polarization of incident line being parallel and perpendicular to the far field director, right, which would correspond to different SPR peaks being contributing more to the appearance of such a sample. Now, this alignment can be achieved on very large length scales, and we can also have defects in this system. And if we have defects, we still can see that the nanoparticle orientations follow the average, spatial distribution of liquid crystal director, right? This is clearly seen here from those scattering images where they are polarization dependent, and what we have in here is a pair of half integer disclinations in director field. Gold nanorods simply follow the director field. Okay, so it's great. We can obtain this type of alignment of gold nanorods, but the question is, can we obtain something a little bit less expected with this system, right? Because we aligned nanorods along the far field director, right? This is, interesting and potentially practically useful, but we know that if we were to have longer rods, we could also achieve liquid crystal even just from rods themselves, right? So there is kind of quantitative difference in what we achieved, but there is not big qualitative difference. Now, what I will show you next is that we can also obtain dispersions of gold nanorods in those lytropic liquid crystals where we will have negative values of scalar order parameter. And this type of ordering of anisotropic colloidal nanoparticles could not be possibly achieved without the use of liquid crystal at all, because entropy, which drives the nematic isotropic nematic transition in Onsager model, would not favor that at all, right? Even at high concentrations. And so, so how can we do it? Well, so in this case, we will use discotic micelles, and those discotic micelles form discotic nematic liquid crystals, where the disks depicted in here align on average perpendicular to the far field director, right? And so when we disperse gold nanoparticles in this system, what we observe is that the gold nanorods align perpendicular to far field director, but there is no preferred orientation, right? In all of the axial azimuthal orientations, perpendicular to far field director are equivalent in this case, right? And so the rods are again parallel to micelles but perpendicular to far field director. And so now we obtain a fairly unusual dispersion where gold nanorods are orientationally ordered, but the scalar order parameter value is negative, right? And I'll demonstrate that this is the case. Again, it's a little bit not clearly visible because of the lightning here, but there are polarizing microscopy textures and scattering textures which clearly depict that there is strong polarization dependence of light scattering in those images, where we have those kind of discotic nematic liquid crystals and gold nanorods dispersed in them. Now, even to see with more confidence that this is the case, we can use polarized two-photon luminescence microscopy, and in this case we use nonlinear optical process of two-photon luminescence in order to tell for sure that scattering comes from gold nanoparticles, could not come from anything else. You can see again, if we do this type of imaging for orthogonal polarizations of excitation femtosecond laser light, we see complementary textures to each other that are then superimposed on this image on the right. And so this tells us that we do have those type of dispersions of gold nanoparticles because, again, we use femtosecond laser light to obtain two-photon luminescence in a tiny volume of the sample by means of this nonlinear excitation process. So this is a schematic that was used to do those type of imaging. I'll not go into details on how it works, but the two-photon luminescence signals is extremely strongly dependent on the orientation of the gold nanoparticle with respect to the excitational polarization of light, right? So in here you can see such dependence taken for a gold nanoparticle with well-defined orientation, and as we rotate polarization of excitation light, we see this type of angular dependence, which is consistent with the fact that this is a second-order nonlinear process, because the dependence is cosine to the fourth power of angle beta between the axis of the gold nanorod and the polarization of excitation light. So from those type of images, we therefore can tell for sure what kind of dispersion we have. So now let us see how we understand this equilibrium alignment of gold nanorods in this discotic nematic system. So again, we expect that surface anchoring interactions play an important role here, but the important difference is that now the boundary conditions for director at the surface of nanoparticle are perpendicular to the surface, right? So director wants to align normally to the surface of gold nanorods. And so we do the similar type of calculation as we did before, obtain the angular distribution, calculate the scalar order parameter, and again for typical values of the anchoring coefficient, we do obtain the values of scalar order parameter in this model that are consistent with experimentally measured using those extinction spectra values of scalar order parameter of minus 0.39, right? And this is the actual distribution of angular orientations of gold nanorods in this dispersion. So you can see that on average they are pointing perpendicular to far-field director, but not perfectly, just because again it's soft matter system, it's not a solid crystal of some kind, and this corresponds to minus 0.39 being the value of scalar order parameter. All right, so now that we have this nice soft matter system that's quite unusual, I would say the question is, do we see some interesting optical properties, right, because of that long-range orientational ordering? And again, as I mentioned before, we can order those nanoparticles on scales of centimeters, right, so or display scales. And so now we can do comparison of FDTD numerical simulations. Again, it's pretty much numerical solutions for Maxwell's equations, and compare the theory and experiment, right? So if you would have scalar order parameter minus 0.5, this would be the type of extinction spectra you would get. There would be no, this second peak in here, for example, for the perpendicular orientations. And so the simple realization is this is not what we observe in experiment, right? This is experimental dependence. So now we can look at experimental dependencies of the extinction coefficient and scattering and absorption coefficients more closely. We can separate scattering and absorption from each other. And this is what we did in here, right? So you can see that for those gold nanoparticles, we mostly have scattering contribution in the extinction absorption contribution in the extinction. Then we can do numerical modeling for the same value of scalar order parameter and obtain a pretty good agreement with those experimental results. So again, the location, the type of peaks we observe, all can be reproduced in simple modeling by using this fact that the order parameter particles are ordered orientational with finite value of scalar order parameter. I understand we had like 10 minutes break, right? So, okay.
Oh, I don't think we have any break.
In the beginning.
I know you started late.
Yeah, yeah. Yeah, so now from those extinction spectra, we can also calculate and we can also experimentally measure the effective medium properties such as refractive index and also optical birefringence. And so as you can see, those are now very different from what we would have in both isotropic dispersion of gold nanorods and in a liquid crystal without gold nanorods, right? So delta N is enhanced 2 to 3 orders of magnitude depending on concentration compared to the optical anisotropy of pure liquid crystal. And it's also now highly dependent on polarization, so you can see how it behaves, how optical anisotropy behaves close to the longitudinal surface plasmon resonance peak in here, and we can see pretty good agreement between the results of experimental results and the results of numerical modeling. And this is the value of average refractive index that correspond to the same type of a sample. We also can probe the imaginary part of refractive index, and so in here you can see comparison between experimental and computer simulated data for the same value of scalar order parameter, and again we can see good agreement. Now, now that we have nematic-like dispersion of gold nanorods with negative scalar order parameter, we can also think about adding chiral dopants. And this would allow us to do spatial patterning of the orientations of gold nanorods in this complex fluid. And so in here you can see what happens when we add chiral additive to this layotropic liquid crystal. So we now obtain twisted structures. And so the micelles are perpendicular to far-field directory, which twists. The gold nanorods are lined perpendicular to the director, which twists, right? And so, however, they are disordered in the plane perpendicular to the director, rotating along the as you go along the helical axis. And so those are dark field scattering images that document this is indeed the case, that were obtained for different polarizations of incident light. Moreover, not only we can obtain ground state cholesteric structures, but also in cholesterics one can obtain, for example, undulating like configurations if we produce if we apply stress, for example, dilate the substrate of the sample. And so in this case, the two cholesteric layers depicted in here start undulating. And so we then see periodic pattern. This is an image in a vertical cross-section obtained by means of 2-photon luminescence microscopy. So you can see that we can spatially pattern the orientational distributions of those gold nanorods on the length scales from micrometers to tenths of micrometers by simply adding the chiral additive, right? And this now becomes quite interesting because as we control the spatial distributions of orientations of gold nanorods, we should also control the effective medium properties, right? The effective medium index that I showed you is highly dependent on polarization of incident light. Now we can go beyond the simple examples of nanorods that I depicted in here, right? So for example, we can work with different gold nanoprisms, nanoplatelets, and the size and also the shape of those can be varied, and then as we would introduce them into liquid crystal, we can control the surface boundary conditions, either tangential or perpendicular, and therefore those particles differently align with respect to the far-field director, right? So here you can see just some examples of nanoparticles that I depicted in here in the top row of images. and how they align in those systems. So now, in addition to, because of the boundary conditions introduced by those nanoparticles, we can not only produce aligned dispersions of those nanoparticles, but we can also localize them in desired locations in the sample. For example, in here I show a spherical microparticle that, as we saw before, generates a hyperbolic point defect next to it. And so if we have gold nanoparticles, like the nanoplatelets or nanoburst you see depicted in here, somewhere in the sample, the elastic distortions that are produced by this big microparticle tend to attract the nanoparticle to the location of the point defect, as you can see in here. And so not only we can localize this particle inside of the defect, but also orient it with respect to the far-field director and with respect to the bigger colloidal particle itself. So one can measure the forces and potential energies corresponding to this type of interaction. But again, as I already mentioned, those interactions arise due to the fact that the boundary conditions on the surface of those colloidal particles and surface anchoring on the surface. So if instead, for example, instead of nanoburst, we use nanorods, they also localize themselves in the topological defect and align perpendicular to the surface of the particle and parallel to the far-field director as depicted in here. Out of those, we can now produce hierarchical assemblies of the gold nanoparticles, right? And together with dielectric spherical microparticles. And so you can see in here examples of configurations that could occur where we have gold nanoparticles interspacing microspheres, and it all self-assembles inside of liquid crystal medium where those particles are the concave nanoprisms that you can see imaged in here by means of electron microscopy. Not only we can localize them in defects produced by other microparticles, but also defects that can be created in liquid crystals by other means. For example, by means of strong laser light that you focus inside of the medium. And so, for example, one director configuration that actually resembles in this part the famous Hopf vibration, but it has also 2 point defects above and below it. So this type of director configuration that can be obtained in cholesteric liquid crystal confined in a cell with vertical boundary conditions is capable of localizing nanobursts that you can see in here in the location of those point defects. And you can see from the frames of the movie in here how such a particle is attracted to those point defects, and then eventually those nanobursts are localized inside of them, right? And so the question is, okay, we can align nanoparticle dispersions in liquid crystals. We also can localize nanoparticles next to bigger particles and also in topological defects, right? So we can control their spatial positioning, but can we also use electric or magnetic fields in order to, and especially electric fields, in order to control their alignment? And so I'll go a little bit quickly through those slides, but the answer is, okay, the answer is yes. So in here you can see dispersions of gold nanorods in a thermotropic liquid crystal, where by means of applying electric fields, we will be able to switch the orientational patterns of those nanoparticles. So again, you can see surface plasma resonance and the angular dependence of extinction. The samples can be aligned on very large areas while exhibiting SPR properties. Now we can control the extinction by applying voltage, and you can see it's only a couple volts that we applying here as we are changing the SPR spectra quite strongly. The response times are relatively slow just because the nanoparticles are much bigger than liquid crystal molecules themselves, so the response of nanoparticle dispersion that we control by means of applying fields is slower than that of liquid crystal itself. And so in here you can see, however, that we can, we can achieve pretty fast racing times, but relaxation times longer of the order of seconds. Now we can change the aspect ratio of the gold nanorods and obtain SPR peak also in the near infrared or far infrared. We can also use nanoplatelets, and those can be dispersed in thermotropic liquid crystals at high concentrations. And here, nanocubes and other shapes, so on. So what I demonstrated tells us that indeed we can use liquid crystal medium, and now I will go, I'll skip a lot more that I had.
Come to the very end, please?
Yes, that's what I do. I will conclude that liquid crystals allow to obtain high quality dispersions of gold nanorods and nanoplatelets and other anisotropic nanoparticles that can be controlled by means of external fields and potentially useful for practical applications. I would like to acknowledge different students and postdocs working on this project, in particular Chinkun Liu, Julian Evans, Bogdan Smalyukh, and Yaoran San. Thank you for your attention.
Thank you. Could you set up?
Sure.
In the meantime, let's see if we can take a few questions for Ivan. Sorry. Go ahead.
Two short questions. Did you consider biaxialities which might play a role for the small nanoparticles? Probably then you wouldn't get these negatives coming from.
That's a very good question, actually. We were thinking about this a lot. And so because we can control the concentration of nanoparticles, we do expect that at very high concentrations biaxiality could be, playing the role, because they would be also aligning, aligning in the plane perpendicular to the far field director, right? But we did not reach yet those concentrations. So the aspect ratios are pretty small, and in order to observe this effect more easily, we plan to play with much longer rods, and maybe in this case biaxial organization will indeed be observed.
I don't see, of course, why it should be as high as ratio, just as the size is small, and the second thing, because which I also want to ask, is about the anchoring. It makes sense that the anchoring is not infinite, so I agree that you need to assume some energy source, but still you get so small value, 10 to the minus 6, which is really weak anchoring, isn't it?
Well, no, it's actually pretty
Ivan will be around for another day. We'll be talking in parallel for the rest of the hour. No. So Ivan will be here tomorrow, right?
Yes.
So I'm sure he'll be happy to answer more questions. Let's get on.
Okay,
Sorry.
Thanks.
Let's get on with Andrew Hiesel from Manchester. Please.